Chapter 19, Building Earth's Surface. So in this chapter, we're going to talk about how the idea of plate tectonics works to build what we see on the surface of the Earth. We discussed it some in the last chapter, and we'll cover some of those things in this chapter as well over again. But the important thing to remember is that plate tectonics is what builds what we see on the surface of the Earth. One way that we know this is using what's called the principle of uniformity. By understanding that the way that rocks are changed by plate tectonics now is likely the way they were changed by plate tectonics in the past. And so if we understand that that process has been working across the Earth for millions of years, then we can understand how what we see today goes back to what was there before. This idea of uniformity, of plate tectonics controlling what the shape of the Earth looks like, kind of replaced previous models where it was thought that catastrophic events like asteroid impacts, because before plate tectonics was understood, that was how it was thought that things worked. It turns out that these events do contribute to what the Earth looks like. Volcanoes, earthquakes, meteorite impacts. They contribute to what the surface of the Earth looks like. But they're not the driving force to everything that we see. That driving force is plate tectonics. So with plate tectonics being the process, the idea of diastrophism, which is basically just the process of deformation that changes the Earth's surface, this is what occurs when the plates move together, move apart, things like that. This produces structures like plateaus, mountains, and folds in the crust. And it comes about from the movement of magma and earthquakes that occur inside of the Earth. So before we can understand how these processes led to what we see on the Earth now, we need to discuss a few terms that we can use in order to describe these different occurrences. The first is what's known as stress, and this is force that tends to compress or pull apart or deform some type of rock. It's something forcing onto the rock. So you can have compressive stress, where you have plates moving together at, say, a convergent boundary. You can have tensional stress, where you have plates moving apart and the rock is pulled apart. Or you can have shear stress, where the plates are sliding past one another and the rock is being pulled in opposite directions. Strain in rock is how the rock adjusts to the stress that it is experiencing. So some rock will experience elastic strain, where it'll snap back into its original shape. Some will experience plastic strain, so that they're molded and bent when they're exposed to stress, and they do not return to their original shape. Or some rocks will just fracture and they'll break. And so stress is the forces that occur on the rock, and strain is how the rock responds. What happens to the rock in response to the stress forces? So again, the possible changes to rock when it is experiencing stress are things like it cannot change at all, or an elastic change where it can recover and go back to its original shape, or a plastic change where it can't recover or it can just break. What determines this is the nature of the rock, things like the temperature of the rock, how quickly those forces are being applied, and how much pressure they're under. And so you can see in general how rocks will behave as the stress goes up. So as you have an increase in stress, you can see some elastic behavior where it'll eventually be able to bend back into its original shape, but at some point it's going to reach what's known as the elastic limit. There, it can no longer bounce back into its original shape. Now it's deformed, and that deformation will continue until it reaches a point where the rock will just rupture and break. The rock formations that we see on the Earth occur because of an interplay between all of these different occurrences of stress and strain on the lithosphere and the crust of the Earth. So sedimentary rocks form from layers of sediment that pile up over time. These are formed from flat sedimentary deposits, and the layers are usually horizontal because they just pile up over time. There's nothing affecting them. However, if some of these rocks are then placed under stress, you can have plastic strain or elastic strain occur, and you see some different types of folds in the rock formations. And so even though these are formed sedimentarily, where you have piles of sediment over time, the stress on these particular rocks have caused them to become misshapen. In some places, the rocks can break apart and the two opposite sides can move independent of one another. There can be some relative movement compared to one or the other. So either one is moving or the other is moving, or both are moving opposite each other. But here you have what's known as a fault. And at this fault, the rocks are slipping past one another. There are different types of faults. You can have what's known as a normal fault, which is where you have a hanging wall that's moved down relative to the foot wall. So the part that is below is above the part that's above it. This hanging wall part, the part above the fault, is slid down. And this can lead to features that you see here like a graben, where you have these normal faults with a piece on the inside, or a horst, where you have the normal faults and the piece in the center is higher. You can also have a reverse fault where the hanging wall part of the fault is moved up above the footwall part of the fault, and this can come about from a result of horizontal compressive stress. Or you can have a thrust fault where you have a really small angle to the fault itself. And the different types of faults and the angles at which they occur, they provide information about what types of stress are producing this rock formation, or did produce this rock formation in the past. Now, in the last chapter, we talked a bit about earthquakes, and earthquakes are the shaking of the ground from a sudden release of energy. And most of these occur along fault planes, where you have one side of the fault displaced with respect to the other side of the fault. One theory for the cause of earthquakes is what's known as the elastic rebound theory, and this is essentially what's understood to be the cause of earthquakes on the Earth. In some region where you have a fault, where you have a break in the rock, where the rocks can move past one another, those two plates will press slightly against one another, and friction will keep those two plates from moving. However, the stress forces will still push on the rock and try to make it move, and that stress will build up. And at some point, the stress will overcome the friction of the rock will break, and everything will move all at once. And when that happens, the whole piece of plate will shift, and it releases a large amount of energy. The stressed rock just snaps back into place, into a new position, and all of the energy is released all at once. And this causes the ground to shake. Now again, where this occurs on a fault, we call the focus, and then directly above the focus on the surface is the epicenter. And we use a seismograph to detect the seismic waves that come about from the earthquakes. And there are three different types of seismic waves. There are P waves, primary waves, which are longitudinal. There are S waves, or secondary waves, which are transverse. And then there are surface waves, which move the surface up and down. We classify earthquakes based on their depth. Many earthquakes are shallow earthquakes. They occur from the surface down to about 70 kilometers deep. And this is where you see about 85% of all earthquakes. Intermediate focus earthquakes are deeper than that, from 70 down to 300 kilometers, and occur somewhere in the upper part of the mantle. Deep focus earthquakes occur even further down all the way to 700 kilometers. These occur in the lower part of the upper mantle and make up about 3% of all of the earthquakes that occur. Now again, we talked about in the last chapter how P waves can travel faster than S waves. That's why they're primary as opposed to secondary. And by using seismographs to measure the distance that these P waves and S waves travel, we can use triangulation to pinpoint where the earthquakes occur on the Earth, so that we can work backwards to figure out where the focus of the earthquake was once it's occurred. There are multiple seismographs buried all over the Earth from all different places. Many of them work together, and they use their data to pinpoint and triangulate earthquakes on the surface. There are a couple ways to measure earthquake strength. First of all, you can measure its effects, how much damage it does to buildings, landslides, how much land is displaced, whether or not tsunamis occur. You can measure it using what's called the Mercalli scale, which is just a relative intensity scale. The scale measures from a 1 to a 12, where you have 1 is an earthquake that's not felt, and a 12 is total destruction with visible ground waves from the earthquake. But possibly the most common way to measure earthquakes is what's known as the Richter scale. And the Richter scale is dependent upon how much the seismograph needle swings, but it measures the earthquake's intensity, and is a logarithmic scale. Remember that the Richter scale, for every increase of 1 on the Richter scale, you have a 10 times increase of earthquake intensity. So a 4 is 10 times more powerful than a 3. A 5 is 100 times more powerful than a 3. And so, based on the Richter scale, an earthquake of a 3.0 would not be felt, and an earthquake of a 9.0 is the largest that we've measured on the Earth. And here you can see what occurs at between each of the different values on the Richter scale. Where above 4 is where you can generally feel the earthquakes and you'll have some damage. 5s and 6s will cause some destruction, and 7s through 9s can cause some major destruction. Some of the most recent and very large earthquakes that have occurred: in 2011, a 9.0 magnitude earthquake in Japan caused a tsunami. In 2010, there was an 8.8 in Chile. And then in the region near New Zealand, in 2010 and 2011, there's some 6 and 7. Just remember to be safe if you're ever in a place where there's an earthquake. If the ground starts to shake, don't panic. If you're indoors, stay away from glass and any type of gas lines and things like that. If you're outside, move away from buildings or things that could fall on you. If you're in your car, stop your car, but stay inside your car so that things don't fall on your head. When it's over, don't try to turn things on. Power lines, gas lines will be broken. Use some kind of way, radio, TV, something to figure out what's going on. Stay off the telephone unless you absolutely can't avoid it. Stay out of damaged buildings. And don't go around looking at destruction, because things can fall on you. Finally, another result of earthquakes are tsunamis. These are giant waves that are generated by earthquakes. They can have speeds of up to 700 kilometers per hour and wavelengths of up to 200 kilometers. And those wave heights can go from 0.5 meters in the deep ocean and reach up to over 8 meters in shallow water. It's about a 2.5 story building.